This is a demonstration of a maze solving program using the breadth first search algorithm. This is one of the more effective algorithms because it searches all of the paths at the same time, unlike the depth first search, which only searches one path at a time. Once it has identified all the cells in the maze, it will start to backtrack using the most efficient route, as you can see here. Okay, so what is breadth first search? Well, if I just close the program and rerun it, but this time at a slightly slower speed, it might give you an idea of how it actually works. So the program's constructing the maze at the moment. So what we're going to do, this is red spot, this is starting position, and I'll start to search to the right, up and down. So every branch it finds, it creates another path and does another search. So we've got maybe 4, 5, 6 searches going on, maybe 7, 8 now. And it will carry on like that. Every time it sees a branch, it will split and start to search that branch at the same time as it searches all the others. This makes it a very, very efficient algorithm. When it gets back to this spot here, this purple spot, it will use the most effective route back to the red spot, which I think was here, the starting position. There we go. Yep. So before I run through the program, I thought it might be a good idea if I just show you the algorithm that I use to create this program. The program you see is written in Python 3. So I've got this little PowerPoint presentation that I'll explain how the breadth first search algorithm works. So I've got this little grid here, a very mini maze. It's only really got 3 or 4 branches. And I'm using 2 lists, a frontier list and a visited list, to store the information, and a variable called content. In fact, there is actually another list called solution, but I'll come on to that in a minute. That creates the backtracking to find the actual solution. But for this part, I'm just only going to concentrate on 2 lists, the frontier list and the visited list, and the variable current. So let's start at the top here. Place start in the frontier. Well, I'm going to use my starting position as number 1. So therefore I'm going to place start in the frontier list. So I place 1 in there. Then I move down to, is the frontier empty? Well, no, I've just put something in it so the frontier isn't empty. So I come across to this side here. Set the current cell to be the frontier. So the current cell at the moment is empty, so it needs to be set to the same variables as in the frontier. So it's 1. And I come down to here and it says move to the frontier, so it's here. So what I'll do, I'll highlight that in red so we can keep track. Highlight in red. Move down. Is the cell to the left visited in the visited list or a wall? Well, the cell to the left is here, so it's in the wall. Okay, so I'll come down to the next part of the algorithm. Is the cell to the right in the visited list or in a wall? Well, this is the cell to my right. It's certainly not in a wall, but it's not in the visited list either. So therefore I move across to this branch here. Place the cell in the frontier queue. So I place the cell, this cell number 2, into the frontier queue. So frontier now has 2 items in it, cell 1 and cell 2. Now move back. Is the cell up in the visited list or a wall? So the cell up is in a wall, and the cell down is in a wall. So ignore that and ignore that. And I place the current cell in the visitors list. So number 1 goes in the visited list. Now I have to dequeue the frontier, which basically means I have to remove the first entry in the frontier list. In Python that's called pop left. I then move back around the loop again. Is the frontier list empty? No, the frontier's still got something in it. So I put the current cell in a frontier list. So the current cell is 1, it now needs to be 2. And I move to the frontier. So highlight that in red. Is the cell to the left in visited list or a wall. The cell to the left is this one here, and it is in a visited list. So I move down. Yes, it's in a visited list. Is the cell to the right in the visited list or a wall? This is the cell to my right, and it's not in the visited list. So therefore, I move to here. Place cell in the frontier queue. So frontier queue now gets cell 3, and I move down to here. Is the cell up in the visited list or in a wall? It's in a wall, and so is the one down, so I can really jump down to place the current cell in the visitors list. So the current cell, which is 2, goes in the visited list. And I do dequeue the frontier. I take out 2. Move up, around. Is the frontier empty? No, it's got 1 item in it still. And I make the current cell the frontier. So it becomes a 3. Cell 3. Move to the frontier. So I'll highlight it. Mark it as red so we know we've been there. Is the cell to the left a wall, or has it been visited? Well, it's been visited. So I move down. Is the cell to the right a wall, or has it been visited? Well, it's not a wall, and it's not been visited, so therefore I move across to the right here, and I place that cell in the frontier queue. So the 4 goes into the frontier queue. Now this is interesting. Now, is a cell up in a wall or in the visited list? Well, it's not in a wall, it's not in the visited list, so therefore I move to the right. Place the cell in the frontier queue. So frontier queue now has 3 entries in there. Is the cell down in a wall or a visited list? Well, it's not in the wall and it's not in the visited list, so move to the right. Place the cell in the frontier queue. So frontier queue now has 4 items in it, 7. Place the current cell in the visited list. So the current cell was 3, so that needs to go into the visited list. Dequeue the frontier. So take out 3 now. No longer required. Move around. Is the frontier empty? No, it's not. Make the current cell the frontier. So the current cell, the current cell gives the frontier. So the frontier is 7, so it needs to be 7. Sorry, the current cell is 4. So that needs to be a 4. Move to the frontier. Move to the frontier. Is the cell to the left? Sorry, I needed to highlight that, didn't I? Is the cell to the left in visited or a wall? The cell to the left has been visited, so I move down. Is the cell to the right a wall or visited? The cell to the right is a wall. The cell up is a wall. The cell down is a wall. So place the current cell in the visited list. So 4 goes in the visited list, into the visited list. I dequeue the frontier, remove 4 from the list. Go up and around. Is the frontier list empty? No, it's not. Make the current cell the frontier list. So current cell, sorry, the frontier is 5, so that needs to be 5. Move to the frontier. So now I'm going up to here to 5, and I'll highlight that because we're going to move to it now. Now, is the cell to the left a wall or in the visitor list? Oh, it's a wall, so I move down here. Is the cell to the right a wall? It is. Is the cell up in a wall or in the visitor list? And the cell is not a wall and it's not in the visitor list, so therefore I move to the right. Place that cell in the frontier queue. So that now gets a 6. Move down to here. Is the cell down a wall or in the visited list? The cell down is already in the visited list. So we move away. Place the current cell in the visited list. So 5. Goes into visited list. I DQ the frontier. I remove 5, no longer required. Is the frontier empty? No. Current cell equals frontier. Let's put that over a little bit. Current cell equals frontier, which is 7. Move to the frontier. Move to the frontier, and I'll highlight that so we know we've been there. Is the cell to the left a wall? It is. So I come down. Is the cell to the right a wall? It is. So I come down. Is the cell up a wall or in a visited list? Well, it's not a wall, but it's been visited. So I come down. Is the cell down in a wall or visited? Well, the cell down is not in a wall and it's not been visited, so therefore I move to the right. Place a cell in the frontier queue. So number 8 goes into the frontier queue. Come down here. Place the current cell in the visited list. Number 7. DQ the frontier. Remove 7 from the list. Background. Frontier list empty. No, it's not. Current cell equals frontier. So frontier is 6. So for the current cell, it must now be 6. Move to the frontier. Move to the frontier, and I shall highlight it. Is the cell to the left in a wall? It is. Is the cell to the right a wall? It is. Is the cell up in a wall or visited? Well, it's not a wall, but it has been visited. Is the cell down in a wall or visited? And the cell down isn't a wall, but it has been visited. So therefore, place the current cell in the visiting list. So the current cell is 6, and I place that into the visited list. I DQ the frontier and go around one more time. Frontier is not empty still, so the current cell equals the frontier. So 6 is replaced by 8. Move to the frontier. I like that. Is the cell to the left in the visitors list or wall? Cell to the left is not in the visited list and it's not in a wall, so therefore place the cell in the frontier queue. So I place 9 in the frontier queue. Is the cell to the right a wall or in the visited list? The cell to the right is not a wall and it's not in the visited list, so therefore move to the right and place that cell in the frontier queue, which is 10. Is the cell up a wall or visited? The cell up is been visited. Is the cell down visited or wall? The cell down is a wall. So we're here right now. Place the current cell in the visited list. Current cell, which is 8, goes in the visited list. And I DQ the frontier. Go back round again. Is the frontier empty? No, it's still got 2 items in there. Make the current cell the frontier. Becomes 9. And move to the frontier. 9. Is the cell to the left the visited wall? Cell to the left is a wall. Cell to the right has been visited, so we can't go there. The cell up is a wall, so we can't go there. The cell down is a wall, so we can't go there. So we place the current cell in visited. 9. DQ the frontier. Or remove 10. Whoops. Remove 10. Back round again. Near the end now. Is the frontier list empty? No, there's still 1 item in there. Place the current cell in the frontier. So replace that with 10. Move to the frontier. You can see now that's the very last item, so all cells have been checked. And if you notice, they're all getting checked at the same time. Is the cell to the left visited or wall? The cell to the left is in the visited list. The cell to the right is a wall. The cell above is a wall. The cell below is a wall. So place the current cell in visited. So the current cell, which is 10, goes in visited. I dequeue the frontier. So now the frontier is empty. Move up here. Is the frontier empty? Yes, it is. And that ends the algorithm. So you can see it's searched across here first. When it got to number 3, it searched there, there, and there at the same time. And then from there to 5 to 6, and then from 7 to 8, and then from 8 it searched both these two paths. So you can see how it does, how the breadth first search works. The algorithm is really efficient. I do like it. Okay, so let me minimize that. Okay, so the breadth first search algorithm explained how we will manage to search all of the cells that are in the maze, but it didn't explain how we got the backtracking part of the program working. So I'm using a different algorithm now. It's called a backtracking algorithm. It's very, very simple. Basically, it uses a key feature of Python's list, which is called a Python dictionary, which consists of 2 key elements. So you have the solution, which is the list name, and you have 2 values. You have a key and a value. So you look up the key and it returns the value. So I'm using this to identify the cell that I'm on and the cell that I came from. So for instance, if I take cell, let's say cell 1 started as a starting cell, so cell 1 came from cell 1, but cell 2 here is the current cell, but previously it came from cell 1. Cell 3 came from cell 2, cell 4 came from cell 3, cell 5 also came from cell 3, cell 6 came from 5, cell 7 came from 3, cell 8 came from 7, cell 9 came from 8, and cell 10 came from 8. So you got this little list of the current cells and the previous cells, and I've just put this really basic algorithm together that allows me to create the backtracking. So first of all, find the starting key, find the key of the starting point. Now the starting point is the very last where you want it to backtrack from. So in this case it's going to be 9, because I want it to go from 9 back to 1. So that's going to be my starting position, and I want it to go back in that direction to the beginning of the cell 1. So starting at 9, I look, that's my current cell, read the value of the key. So the key is 9 and the value is 8. Now make the value the new key and find the new key. So if the key is 9, the value is 8. I now make 8 the key, which is there, and I find the value of that, which is 7. I make 7 the new key and find the value of that is 3. I find the value of 3, so the key of 3, and the value of that is 2. I make that the new key, that becomes 2, the value is 1, and that becomes a new key, and that's 1. So it takes you back in this direction. Very simple algorithm, but very effective. Okay, just to prove the algorithm works from any cell, let's take cell 6 this time. So we say that the key value is 6 and the value is 5, and we convert the value from 5 to the key of 6. That takes us to 3, and 3 takes us to 2, and 2 takes us to 1. So it works in that direction. Let's try 10. So 10 takes us to 8, 8 takes us to 7, 7 takes us to 3, 3 takes us to 2, and 2 takes us to 1. So the backtracking works in any permutation you can choose. Okay, so let me now move on to the actual Python program, and I'll show you how I've coded it to give you the results of a breadth first search. Right, this is the Python program that I wrote to demonstrate the breadth first search, or BFS as it's sometimes called. This first part of the program is used to set up the turtle graphics. Now, as you probably noticed, that the maze and all of the animation is using turtle graphics, and this first piece of the code is just setting up the turtle screen really. So the walls are defined as a white square, the BFS search is defined as a green square, the blue square is the end point, and the red square is a starting point, and the yellow, well, that's the backtracking path. So the first part really just sets up the turtle graphics. Then we come down here, we have various grids I use when I was setting up and testing the program, but the one that I used to demonstrate was grid 1. And this part of the program here, set up maze, just really constructs the maze. So if you look up here, the maze is made up of ASCII characters, and what the program does, it examines each line, and in each line examines each character, and if it sees a cross, then it knows it's a wall. If it sees a S, then it knows it's a starting point and puts in a red square. If it sees an E, it knows it's the end point and puts in a blue square. So that's basically what this part of the program is doing here. So if it sees a character and it's a cross, then it stamps it with a white square. If it sees it as an E, then it stamps it with a blue square, and so on. Now this part of the program, this is the algorithm that I was going through earlier on. Now unfortunately, Turtle Graphics doesn't use a nice convenient 1, 2, 3, 4 for its cells. It uses a grid system. So each cell has a X parameter and a Y parameter. So if you look in here, and this part of the program here where it says checking to the left, X is the actual cell it's in, and if it's checking left, it's going to go -24 on the X-axis to see if the cell to the left of it is in the path or as is in the wall. So unfortunately it can't be nice and convenient as in terms of having 1, 2, 3, 4, but it uses the grid system. So that's why you're seeing a lot of X and Y's plus and minus 24s. So that's searching left, this is searching down, this is searching to the right, and this is searching up. The code inside each of these paths is exactly the same as it was with the algorithm I showed earlier on. This part of the code is the backtracking routine. Fairly straightforward, not much to say about that. I explained that earlier on. These pieces of code are setting up the various lists that we used in the program, and these are the three main routines: set up the maze routine, the search routine, and the backtracking routine. Now this code is available on GitHub if you want to. There's a link below in the description. Please feel free to download it, play around with it, do whatever you want with it. So I think that's about all I wanted to say. Maybe I'll just run the program again, just so get a feel for how it works one more time. So the turtle graphics are constructing the maze. There's the BFS search going through. And there we go, there's our back path. And just to prove that I'm not cheating, let's quickly change the start on. So the start is here. Let's move the start to another location. To say, I don't know, here. And let's move the end somewhere else as well. To say, yeah. And I'll run the program again, see what happens. Okay, so our start is over here now. And where did we put the end? Somewhere around here, wasn't it? Yeah, there's the end here. Okay. So the BFS is taking a different route this time, obviously, because the start position is different. But you still create the most efficient backtracking path. There you go, bang, done. So you see, it will work in wherever you put the start and end points. The program will work. It's a really efficient algorithm. Okay, thank you for listening. Hope it was of use to you. Bye for now.